So we've talked about means and standard deviations, and now we want to talk a little bit more about data points themselves. Specifically, how can you figure out where a data point lies within a data set? And how can you tell if a particular data point is actually an outlier or not? So we're going to start off with a definition for something called a z-score, and this is a concept that we're going to see a few times throughout the semester. It's sort of an important one. And what a z-score is it's a measurement, it's a number that's going to measure how far away from the mean your particular data point is. And if your z-score is positive, it would indicate that your data point sits above the mean or to the right of the mean. And if your z-score is negative, it would indicate that your data point sits below the mean or to the left of the mean. So what it is, it's a measurement in terms of standard deviation. So we're going to take the data point, whatever it's measuring, whether it's measuring height or weight or number of people or whatever it happens to be measuring, we're going to convert it into a standard deviation number. So we're going to take the data point itself, x, we're going to subtract the mean for the whole data set. That tells us how far away from the mean the data point is. And then we're going to divide by standard deviation to convert this to a standard deviation type number. Now, there's two formulas here. One of them uses sample notation. See all the English letters here for mean and standard deviation? And then the other one, it's essentially the same formula. It just uses Greek letters for mean and standard deviation. It actually doesn't matter if you're dealing with a sample or a population. It really is irrelevant because the formulas will be exactly the same thing. It's sort of standard procedure that we're always going to round our z-scores to 2 decimal places. That's sort of the standard MO for z-scores. So let's try an example involving baseball. It says, determine whether the LA Dodgers or the Boston Red Sox had a relatively better run-producing season. And it's this word right here. It's not necessarily who did better. It's important that it says who did relatively better. So we have some information about the Dodgers and we have some information about the Red Sox. The Dodgers scored 804 runs, and they play in the National League, where the mean number of runs was 710.8 and the standard deviation was 60.2. Now, the reason they're using population notation is because we have access to all of the teams in the National League. And well, for Major League Baseball in general, we have access to the entire population, so we can use population notation here. The Red Sox actually play in a different league, though. They play in the American League, where you can see that the mean number of runs is different. It's 731.2, and the standard deviation is 72.6. We can see that the American League had a higher mean, but they also had more variation, so their data points were more spread out than the data points for the National League. Because these two teams are coming from different leagues, you can't just say, well, 876 is better than 804, done, right? That doesn't involve any statistics. That's comparing apples to oranges, and we can't do that because they come from different populations. We need to standardize so that we can compare them, so they need to be on the same scale, and that's what a z-score is going to do for us. So let's look at the Dodgers first. And let's write down what we know. For each of these, we should have an x, a mu, and a sigma. So it's really helpful if you'll organize and pull out the numbers so that you don't have to read so many words. So the Dodgers had 804 runs. Their mean was 710.8. Their standard deviation was 60.2. That's for their particular league. And then over here, I'm going to talk about the Red Sox. I'm going to do the same thing, x, mu, and sigma. So they had 876. The mean was 731.2. I can't tell you how much I think it's going to help you if you guys would organize it like this. Okay. All right, now what we're going to do is we're going to look at the z-score for each one. So for the Dodgers, the z-score is going to be, you always start with the data point, you subtract the mean, and you divide by the standard deviation. Now you have to be careful on your calculator If you want to type this in one shot on your calculator, you need to use parentheses along the top. Otherwise, it'll only divide the 60.2 into the mean, and we want it to divide into both. So let's see what we get here with this. We have 804 minus 710.8 over 60.2. And let's see what the z-score turns out to be for the Dodgers. We're going to round to 2 decimals, so I'm going to call that 1.55. So that would be the z-score for the Dodgers, meaning that 804 runs is 1.5 standard deviations above the mean. So now we know exactly where they're sitting with respect to the mean, and I'll draw a picture here in a little bit. All right, let's do the z-score for the Red Sox. I'm going to start with the data point, 876, subtract the mean, divide by the standard deviation. And both of these teams did better than the average, and so I know the z-scores are going to turn out to be positive. Put it here. All right, did I get that typed in there right? Yes. Okay, so this z-score is 1.99. So they're sitting almost 2 standard deviations above the mean, just right before 2 standard deviations. So if you wanted to think about a picture, if we were, assuming that these were bell-shaped, and we had a little picture here, the mean, how far is the mean from the mean? Well, it's 0 away from itself, so that z-score would be 0. And then if you go up 1 standard deviation, that's where 1 would be. And if you go up another standard deviation, that's where 2 would be. See, these z-scores are measuring how many standard deviations. And if you wanted to go the other direction, this would be a -1. And you'd have a -2, right? So let's see, the Dodgers at 1.55 would be sitting about right here. That's where the Dodgers are sitting. Right there. That's a D for Dodgers. Okay, 1.55. But the Red Sox are sitting at 1.99. I'll put a little R for Red Sox. That's where they're sitting. So you can see who's farther away from the mean. And in this case, better means farther away. Well, the Red Sox are farther away from the mean. And so that one is higher. And so the team that had the relatively better run producing season was actually the Red Sox, but not because 876 is bigger than 804, right? Like, an elementary school kid that doesn't know anything about statistics could figure it out if that was as easy as it is, but we actually have to compare z-scores. So we are going to say the Red Sox had a relatively better run producing season because, if we want to justify this, their z-score was farther above the mean. I'll say it was larger, which means it was farther above the mean. All right, so in that case, it would mean better. There's certain times when the larger the number, it's not better, like in golf, like the larger your score, the worse you actually did. But for most other sports, it's higher is better. So that's how you do z-scores and how you can compare the relative positions. But again, we're having to standardize these things to z-scores so that we can actually compare them because they're coming from 2 different populations. Now, the same thing happens when we start talking about heights of men and women. Just genetically speaking, men have a larger frame, so men are taller. And so when we compare heights for men and women, that's again like comparing apples to oranges. So we have to standardize the scale down so that we can actually compare them. So this says the average man in his 20s is 69.6 inches tall. That's about 5'9.5", with a standard deviation of 3 inches. So that means most men their heights vary about 3 inches from the average on average. Okay, so give or take 3 inches, that's where most people fall. The average woman in her 20s is 64.1 inches tall, that's about 5'4", with a standard deviation of 3.8. So you can see the men's average is higher, but the women's heights vary more than the men's heights do. Who is relatively taller, a 67-inch man or a 62-inch woman? That's what we want to know. Who is relatively taller? So again, I'm going to set up, I'm going to have the man here, and then I'll have the woman over here, and you need to have an X, a mu, and a sigma for each one. And you just have to read and fill in the numbers. So it's a 67-inch man, so he's 67 inches tall, that's like 5'7". Mean is 69.6, standard deviation 3.0. So you can see he's shorter than the average, so his z-score is going to be negative. The woman is 62 inches, average is 64.1, standard deviation 3.8. You can see she's also below average, shorter than average. Okay, z-score. Data point minus the mean over the standard deviation. Let me just write them all out and then I'll go to my calculator. Data point minus the mean over the standard deviation. And let's see what we get. Okay, so for the man, negative, like we said it was going to be negative. And if we go 2 decimals, we need to round that to 0.87. So negative 0.87. That means that he falls 0.87 standard deviations below the mean. That's where he would fall. And then for the woman, negative 0.55. So she's about a half a standard deviation below the mean. And let me again kind of draw a picture here. So again, if we're assuming that their heights are bell-shaped, if this is 0 and this is -1, right here, put an arrow, that's the man, negative 0.87, so almost to -1, but not quite. And then the woman would be right here, negative 0.55. So in this case, we're trying to figure out who's relatively taller, so who's further on the right, and it would actually be the woman. So because she's closer to the mean, and in terms of height, the man is more below the mean than the woman is. So that would make the woman relatively taller. And it says explain your choice using a complete sentence. So the woman kind of the same reasoning. Her z-score is larger. So negative 0.55 is bigger than negative 0.87. So that would make her actually taller because her z-score is larger. So that's how you compare z-scores.